Welcome to The Explainer. Today, we're diving straight into the monumental mathematical puzzle happening right behind your smartphone screen. Every time you ask for directions, you're actually kicking off one of the most fascinating computational battles in human history. Let's get right into it.
To really grasp the sheer scale of this puzzle, just think about the number of possible routes from, say, New York to San Francisco. With over 64 million distinct intersections in the North American road system alone, a simplified estimate gives us 10 to the 220 possible combinations. I mean, to put that into perspective, even if a supercomputer could check a billion routes every single second, finding the absolute shortest path using brute force calculation would take well over 10 to the 200 years.
And yet, despite that practically infinite maze of possibilities, modern navigation apps spit out the absolute fastest path in roughly 4 seconds.
So how on earth is that even possible? That's the crucial question we're exploring today. How do we jump from an impossible mathematical bottleneck that literally should take longer than the lifespan of the universe to the instant directions you and I rely on every single day?
Moving on to Dijkstra's 20-minute invention. To figure out how this works, we actually have to travel back in time to an Amsterdam coffee shop in 1956. Here, a brilliant computer scientist named Edsger Dijkstra was simply trying to prove to the world that early computers weren't, well, totally useless.
You know, what's genuinely fascinating is just how little faith the general public had in computers back then. When Dijkstra tried to get married, the municipal authorities flat out refused to accept programmer as a real profession. He actually had to register under the ridiculous entry of theoretical physicist instead. So facing this extreme skepticism, Dijkstra knew he needed a relatable, everyday demonstration to impress non-mathematicians. He decided on a simple, shortest path problem between two Dutch towns.
Sitting at that cafe, he solved this routing problem without even picking up a pen or paper, inventing a full solution in just 20 minutes. His brilliant algorithm works kind of like a ripple in a pond. Step 1, you set the starting point's travel cost to 0 and all other intersections to infinity. Step 2, you explore the immediate neighboring nodes and update them to the lowest travel cost. And Step 3, you jump to the next lowest cost unexplored node and branch out again. It's an elegant step-by-step process that continually expands outward, checking and updating shortest paths until it confidently hits the destination. But, of course, there's a massive catch. Dijkstra's algorithm blindly searches in all directions. If you want a simple trip from Newark Airport to the Central Park Zoo, the algorithm wastes precious computing time scanning something like 65,000 intersections. It just pushes outward in this massive circle, exploring completely wrong directions, including large swaths of New Jersey and Staten Island, before it ever even gets close to the zoo. Which brings us to directing the search. This 65,000-node problem brilliantly illustrates why modern systems, which have to handle millions of simultaneous user requests, desperately needed to upgrade this 1950s math. We essentially needed a way to give the computer a sense of direction.
Enter the A-star algorithm. This is a modified search formula that uses heuristics to penalize searching in the wrong geographical direction. Think of a heuristic like a straight-line physical distance pointing directly to the target. By heavily favoring intersections that physically get closer to the destination, A-star aggressively pushes the search frontier forward. Fun fact, this is actually a widely used method in video games like Minecraft to help non-player characters navigate mazes.
But when we pit these two approaches against each other for road maps, a major flaw emerges. If you're optimizing purely for physical distance, A-star is the clear winner, exploring about 10 times fewer nodes than Dijkstra. But mapping apps aren't just about distance, right? We care about travel time. And accounting for speed limits completely ruins A-star's computing efficiency. It forces the computer to run some really nasty square root math that heavily bogs down the processor. So for travel time, a well-tuned Dijkstra actually beats A-star.
So engineers tried a totally different approach, bidirectional search. Instead of one massive ripple from the starting point, what if we search from both the start and the destination simultaneously until they just meet in the middle? This simple tweak is surprisingly effective. A basic search from Carnegie Hall to Wall Street drops from a massive 7,200 node search area down to just 2,600 nodes. Now let's look at the hierarchy of roads, because even searching from both directions lacks a vital component, and that's human intuition. The algorithm simply doesn't understand that major highways are inherently faster than meandering, twisting local roads. It treats every single road as an equal possibility. Back in the 1990s, early GPS systems tried to solve this with a manual hierarchy. Surveyors literally went out and labeled roads by hand as express,
major, or narrow. The algorithm was then forced to step up this strict hierarchy, searching narrow roads first, then bumping up to major roads, and finally highways. But this was incredibly rigid. If the map's initial candidate search area was set too small, you risked missing much faster local shortcuts entirely, simply because the computer wasn't allowed to look at them.
Moving into the pre-processing secret. Let's see how all of this builds into the exact magic that powers the 4-second route on your phone right now. Because engineers desperately needed a way to perfectly balance lightning speed with absolute accuracy. To achieve instant results, mapping companies knew they couldn't just pre-calculate a massive brute force lookup table of every possible shortest route in North America. Generating that master list would literally take over a decade of continuous computing on a single core and require 8 petabytes of storage. That's like storing all of Wikipedia 16 times over. Oh, and the entire thing would need to be rebuilt from scratch every time a single road closed. Not going to happen.
Instead, modern algorithms pre-process the map using something called nested dissection. They mathematically cut the country in half over and over, identifying massive geographical bottlenecks. For example, they identify the Mississippi River as the top 102 bottleneck nodes in the country, simply because to get from east to west, you have to cross it. Then they cut the east along the Ohio River and Appalachian Mountains and the west along the Rocky Mountains. They continuously rank these crucial bridge nodes by priority.
And this ranking creates what we call customizable contraction hierarchies, or CCH for short. It's a brilliant system that inherently knows exactly which intersections matter most. It links these highly ranked nodes with artificial mathematical shortcuts. This preserves the precise travel cost of local shortest paths, but heavily limits the search area. So the live search can now aggressively jump straight to the highway level without ever worrying that it missed a faster backroad shortcut.
The performance metrics on this are absolutely incredible. By taking just an hour or two to pre-process the map's hierarchy in the background, the actual on-the-fly search is condensed from checking 64 million nodes down to just 1,450. And the runtime? It drops from 7 sluggish seconds down to 200 microseconds. That is a 35,000 times speed improvement, making it perfectly capable of handling millions of users instantly.
Bringing us to our final section, a lasting legacy. Though modern routing applications use these incredibly fast, complex contraction hierarchies to give you instant directions, it is absolutely amazing to realize that at their core, they are still running Edsger Dijkstra's brilliantly simple search algorithm from 1956.
Dijkstra famously said, "Simplicity is prerequisite for reliability." When he designed his original code, he explicitly avoided using pencil and paper. He found that designing entirely in his head forced him to avoid all avoidable complexities. It's exactly that ethos of pure, stripped-down efficiency that keeps his foundational work relevant nearly 70 years later.
He deeply believed that the programmer, not the machine, was ultimately accountable for the elegance and thoughtfulness of the final product. He always hoped his focus on elegant problem-solving would outlive him, guiding the hands of engineers for generations. As we wrap up this explainer, I'll leave you with this provocative thought on your own work. Even if you only control a little corner of the world, how can you make it as elegant and thoughtful as possible for the people who come after you? Because as we've seen, brilliant, simple foundations can genuinely change the world. The next time your phone seamlessly guides you across the country, just remember the elegant math and the theoretical physicist making it all possible.